All right, we'll get going today. So today's a milestone day because we're gonna finish. We're gonna finish the course today, although we still have review stuff obviously coming up. But we'll get through the last new material that you'll need for the final exam. So we'll get to that by the end of today. As I've been reminding you a few times already, the final exam review session is going to be Friday and Monday. So we'll do part of it Friday at 1 p.m. this week, and then on the very last day of class, we'll finish it. All right, so you've seen this a few times now, so nothing new there. Both of those review sessions will be recorded, and I think the questions should already be posted in Blackboard if you want to get a head start on those. I think that's the only major announcement that I have. Everything else is just related to what's coming up. The sign-ups for the final exam began today, I think. So if you haven't gotten a time for that, if you have a specific time you want, try to get it early. So the exam is offered starting on Wednesday of next week, which is May 2nd, through Saturday. I think there's also Saturday times available if you prefer. So that'll be something you want to take care of as soon as possible to make sure you get a good time. All right, so we're going to move on, and the last thing we're going to talk about in this course is phase diagrams. So we've been talking about the different phases of matter through chapters 8 and 9, and now we're starting to talk about phase changes. And the topic we introduced last time about vapor pressure and vaporization and all those things, we kind of understand that by now that changing the temperature of a substance can alter what phase it's in. So we can go from solid to liquid, liquid to gas by increasing the temperature. The other thing that affects the phase of matter is the pressure that it's in of its environment. So we kind of learned about that with vapor pressure. We saw that the boiling point of a substance occurs when the vapor pressure equals the atmospheric pressure. So if we change the atmospheric pressure, the boiling point is going to change, meaning that we can change from liquid to gas also by influence of pressure. So this is what a phase diagram shows us, is that it's going to show us the different conditions of pressure and temperature under which the substance exists in different phases of matter. So what it is a temperature pressure diagram. So those are the two axes, as we'll define a little bit later, and we'll see. So it's a temperature pressure diagram. So each substance has its own phase diagram, every element, every pure compound. And something you'll talk about in Chem 2 is that you can also have phase diagrams for mixtures as well. And what it shows is the conditions under which that substance exists as different phases. So you can look at a phase diagram, you can pick out a temperature and a pressure, and you can use that diagram to tell you that substance will be either a solid, a liquid, or a gas at that temperature and pressure. So that's what it allows you to do. So the axes are pressure and temperature. You're going to put pressure on the y-axis. Conventionally, it would work. The diagram would work the same either way, but conventionally you have y-axis is pressure, x-axis is temperature. And then what you're going to have is you're going to have some lines and curves on the diagram that separate the different phases of matter, solid, liquid, and gas. So you're going to have different regions on the diagram that correspond to each phase of matter. So in a simplest phase diagram, you would just have three regions, solid, liquid, and gas. Although, as we'll see, sometimes when you have, with certain substances, you'll have different phases present for solids. So sometimes there's going to be multiple solid phases present. The one that we'll see today, and the one that we're already kind of aware of, is carbon. We know that carbon can have two different phases, diamond and graphite, and both of those then will be shown on the phase diagram. So in many cases, and this is very common for a lot of metals and ionic compounds, especially metals, you'll see different regions in the phase diagram that correspond to different phases for the solid, which basically means different crystal structures for that solid. So we talked about how metals can, some of the common crystal structures for metal are the simple cubic and the face center cubic, body center cubic, those things. In some cases, with a lot of metals, they'll exist with two or more of those different structures under different conditions. So on one temperature and pressure, there'll be face center cubic. At another temperature and pressure, there'll be body center cubic. And a phase diagram would show all of that. So if there's multiple solid phases, you would also see that. We're not going to get into really complex phase diagrams in this course, but at least one of the ones we'll show today has two different solid phases present. And then why they're useful is that they allow us to predict phase changes and a lot of different things about a substance besides that. So we can predict which temperatures and pressures phase changes will occur at. Allows us to predict vapor pressures of substances and many other properties under a wide range of conditions. So it's a very visual way of representing a lot of these phase change properties and things that we've been talking about recently in this course. Alright, so that's why phase diagrams are useful. One of the fields that they're especially useful in is metallurgy, which is casting metals and alloys in different ways. And phase diagrams are helpful because they allow you to predict what temperatures you have to go to melt the metal at a very simple level, and then also what conditions you would need to access different phases of that metal if that's important. So phase diagrams are used a lot in many industrial applications as well. They're not just a sort of a general chemistry curiosity. So the best way to learn phase diagrams is just to look at some and talk about then the different properties and different features that they have. So this is the phase diagram for water, one that we'll see a lot. And so what we have for water is, again, you have these different lines and curves that divide it up into, in this case, just three regions. So when you go to, and we can think about this a little bit conceptually, if we go to low temperature, which is to the left on the x-axis, and high pressure, which is top to bottom, which phase of matter do we think would exist under those conditions? Just take your guess. Solid. Okay, so as we go to lowest temperatures and highest pressures, we're in the solid region, so that region all the way to the left of our diagram is solid. And then if we go to high temperatures and low pressures, that's going to be our gas region. And then the one that's in the middle would be our liquid region. So again, these lines on the diagram divide up the solid, liquid, and gas regions. And then we can talk about some of this in a little bit more detail. So I'm going to highlight in red here this line here. So the one that I highlighted in red is the solid, liquid line. And we would use that line to predict the melting point at a variety of pressures. So we know that the normal melting point of water is 0 degrees Celsius, but we see that the solid liquid line has a little bit of a slope to it, telling us then that the melting point would be a little bit different if you go to different pressures. It doesn't change a lot. You can see that this line is almost vertical, but it does slope back a little bit, meaning that if we increase the pressure or decrease the pressure, we're going to have a slightly different melting point than 0 degrees Celsius. And so by looking at where we are in this line, we can predict the melting temperature at any pressure as we go along this line here. The other line that we have in this diagram that divides the other two phases, this one here, is the liquid gas line. So as you might have guessed, this allows us to predict boiling point. We see that this one does change quite a lot as a function of pressure. So this is our liquid gas line, which allows us to predict the boiling point. Now we learned last time how to do that mathematically. We talked about that equation that relates vapor pressure to temperature. And so if you knew the enthalpy of vaporization and you knew which atmospheric pressures you were talking about, you could predict boiling points using that equation as we did last time. But this allows you to do it in a sort of a pictorial fashion, in a graphical sense. So as we go along this line, as we increase the pressure, we see that the boiling point will also increase, as we kind of already know. So following this line, we can predict the boiling point at any pressure. And then we're going to label some important points on this diagram that allow us to talk about the normal boiling point and the normal melting point. So we know that normal boiling point and normal melting point occur at 1 atmosphere of pressure, which is on this diagram in millimeters of mercury to 760 millimeters. So if we draw across there, that's And so this point here, which I'm labeling as A, that's where the solid liquid line crosses 1 atmosphere of pressure, so that's going to be our normal melting point. Which we see extrapolates down to about 0 degrees Celsius, assuming I drew that right. And then this other point here on the diagram, where the liquid gas line crosses 1 atmosphere, that's going to be our normal boiling point. I'll label that as B. So if we see the temperature value that corresponds to that point, that'll give us the normal boiling point for the substance, which we know for water is 100 degrees Celsius. So you can use phase diagrams to predict normal boiling points and normal melting points by just figuring out where these two lines cross the 1 atmosphere horizontal line that I've drawn here. Or alternatively, we could predict boiling points and melting points at any other pressure that we'd be interested in as well. And that's what this diagram quickly allows us to do. So that's kind of some of the features of a phase diagram. Any questions on those basics before I move on to a little bit more complicated things about this? All right, so let's talk about a couple other things that we can get from a phase diagram. So I have a sort of a smaller version of the one we just looked at. So the first thing we notice is, and this one it's a little bit more exaggerated, maybe easier to tell, we see that our solid liquid line has a negative slope. So if you see it's not quite vertical, it's a negative slope. It's going in this direction a little bit. So what does this indicate to us? So if we increase the pressure of our sample, so let's say we start here, this is our solid, liquid, and gas regions again. So let's say we start here in the solid region, really close to the solid liquid line. If we go straight up in pressure, to the best of my ability to draw a vertical line, we see eventually we're going to cross over into the liquid region of the diagram. So that's not a perfectly straight line, but because the slope of that solid liquid line is negative, as we go straight up in pressure, keeping the temperature the same, that means that we can as we increase the pressure, we convert from solid to liquid. And what does that tell us then? If we increase the pressure, we're packing the substance together more, we're compressing it, and that means then that our liquid is more dense than the solid, because as we go to the higher pressure region where we're compressing the substance, we go from solid to liquid, and that tells us that liquid is more dense than solid for water. Now this is actually not the most common situation. Usually the solid is more dense than the liquid, but water is one of the rare examples, and that's why ice cubes float in water, is because they're less dense than water. And so we see that as we increase the pressure. And so the slope of this solid-liquid line tells us then which of the phases between solid and liquid is more dense. In this case, it would be the liquid that's more dense. We can maybe see that a little bit clearer if we go to the bigger diagram. So we see that, again, our solid-liquid line has a negative slope. So if we start here just on the left in the solid region, at that position, and we go straight up in pressure, eventually we cross over into the liquid. So if it was more exaggerated to be able to tell. But anyway, we cross from solid to liquid as we increase the pressure, telling us that the liquid is more dense than the solid. Sorry, I thought I lost my notations. Now the other point here that I haven't talked about yet is called the triple point. That's marked here with an O. I don't know why they marked it with an O. I'll mark it with an X just so you can see it better. So anyway, the triple point, which I've marked with an X using my handwriting, that's the point at which the three phases converge, or all three of those lines converge. And so at that condition of temperature and pressure, the solid, the liquid, and the gas can all coexist. That's the only conditions under which all three phases can coexist for that substance. So that's where that intersection is of all three of those lines. So under these conditions, the solid and liquid have the same vapor pressure. Which is why then you can have solid, liquid, and gas together, because they both have a vapor pressure associated with them, and all three can coexist. All right, so that's the triple point for water right there at close to 0 degrees Celsius and about 4.5 millimeters as is marked here. So that's the triple point, which is the intersection of those three. And then the last one to talk about, you'll notice in these phase diagrams that we draw, this liquid gas line, which allows us to predict boiling point, eventually it just ends. It just stops. And so the end of the liquid gas line, which I'll mark with the letter Y, we call that the critical point. Okay, so the critical point is the point at which the vapor can no longer be liquefied. Or another way to think about this is once you go beyond that point in temperature and pressure, you no longer are able to distinguish liquid and gas phases. You can no longer convert between liquid and gas. You just have one phase present beyond that. So beyond this point, we don't have separate gas and liquid phases. We have what's called a supercritical fluid. So beyond the critical point, which is this top part of the liquid gas line here, the gas and liquid phases are indistinguishable and they exist as what's called a supercritical fluid. Supercritical meaning above the critical point. I'll put the whole thing in quotes. Supercritical fluid. Alright, so essentially that's the point where we no longer have two separate phases. We just have one phase called a supercritical fluid that exists when we go beyond that. Yes?
Isn't liquid more dense than solid?
Yes. Jeez. Again, my ability to talk and write at the same time is questionable. There's another case where it was. Yeah, so liquid is more dense than solid. That should read solid, not liquid more dense than liquid, of course. Yeah. Jeez, what did I do now? Oh yeah, man, you guys are hammering me today. All right, so they have the same vapor pressure. All right, I'll get it together. Don't worry. All right, so we have those features as well that we can read from a phase diagram beyond just where the phase changes occur. So let's look at another example of a phase diagram just to see some slight differences that can exist. So let's look at carbon dioxide, CO2. And this introduces a concept which we haven't seen yet called sublimation. So what we notice in the CO2 diagram is we have, again, the same regions. Solid is going to be lowest temperature, highest pressure. Liquid in the middle. And then high temperature, low pressure is the gas region. So that doesn't change. Those regions are going to be, for any phase diagram that only has three regions, that's what they're going to look like, solid, liquid, gas, in that sort of order. But there's a couple differences here. The first thing that we notice is that if we're at 1 atmosphere, in this case 1 bar of pressure, which is very close to 1 atmosphere, what we see is that if we have solid CO2 and we cross over and increase the temperature at a constant pressure of 1 atmosphere, we go directly from solid to gas. So this process of going directly between the solid and gas phases without going through the liquid phase is called sublimation. All right, so that's another type of phase change that we haven't really seen much yet. So that process of converting a solid directly to a gas is called sublimation. So what we see from this diagram is that if we're at 1 atmosphere, normal atmospheric pressures, or 1 bar as is indicated on this diagram, we see that CO2 sublimes at about minus 78 degrees Celsius. And this is likely something you've encountered in your everyday life. So what we see is that if we cool down CO2 gas to minus 78, we cross the gas solid line and we go from gas directly to solid. And you know that solid CO2 is referred to as dry ice. So if you've ever played with dry ice before or seen it, it doesn't liquefy when it gets warmed up. It just goes directly to the gas phase, and that's because in the phase diagram of CO2, the solid-liquid line exists below, or at 1 atmosphere below this triple point there, and that's where you have sublimation occurring. So that solid-gas line, that division between those two phases, which very often exists on a phase diagram, at least under some conditions, that's going to tell us then under which conditions we would sublime the material. Sublimation occurs in that region. Now what you'll also notice is that sublimation can only occur when we're at temperatures and pressures below the triple point. So your triple point is right there. That's where solid, liquid, and gas all coexist. If we go to lower pressures than that, that's the only place where we can have sublimation. So that's another thing that your triple point tells you is if you want to have sublimation, you need to be below the pressure that corresponds to your triple point. Anything above that pressure, you would go between solid and liquid before going to gas, as more conventional. So sublimation only occurs at pressures below the triple point. So that's another important feature of this. And then the other thing we notice for CO2 is that we have a different slope. Our solid-liquid line in this case, which only occurs at much higher pressures than 1 atmosphere, we see that that has a positive slope. So that's one difference between CO2 and water besides sublimation. So that means the solid in this case is more dense than liquid. Alright, so if we start here at a liquid and we increase the pressure at constant temperature, we see we cross from liquid to solid, and that means as we compress the material it goes from liquid to solid, telling us that solid is more dense than liquid, which in most materials is probably the more common situation. The opposite scenario that we had in water is not particularly common, where the solid being less dense than liquid, but for CO2 we see that it's more of the normal expectation, solid being more dense than liquid, which makes sense because in a solid the atoms and molecules are packed together tighter than they typically are in a liquid. Okay, so that's some other features of phase diagrams that we can see by looking at CO2's diagram. The last one I'll show you is the one example that we have that I'm going to give you that has two different solid phases. So if we go to the phase diagram for carbon, we know that carbon has two different solid phases that we're familiar with, diamond and graphite. And so you see that the phase diagram becomes a little bit more complicated. Now again, if we go to the highest temperatures and the lower pressures, that's still going to be gas. And if we go in this region, that would be the liquid region. But we see on the left side of the diagram, the lowest temperatures and highest pressures, we have two different phases. We have another line that divides the two. Now there's no easy way to predict which phase is which, at least based on the knowledge that we have, but the one that's way up here is diamond, and the one that's at lower pressures is graphite. Now this is interesting if we think about it here for a second, because you have to go to really high pressures to convert graphite to diamond. So at very high pressure we could convert graphite into diamond. So we have to go to, it looks like about anywhere above like 10 to the 9th Pascal, which is a huge pressure. We can convert graphite to diamond. So there are some ways of making synthetic diamonds where you take another source of carbon and convert it into a diamond by going to really high temperatures and or pressures. But it's very expensive and very difficult to do that, so that's why the diamonds that we wear as jewelry still typically are dug out of the ground and not made from graphite. Now the other thing that this tells us is we see that when we're at normal atmospheric conditions, so down around here, 1 atmosphere and temperatures that we exist in, we see that the most stable form of carbon is graphite, not diamond. And so you've probably heard the advertisements. I don't know if they still have this slogan or not, but the diamond manufacturers, they say a diamond is forever. And that's certainly false advertising, because if you have a diamond and you just let it sit there for forever, it will eventually convert into graphite, because graphite is the more stable form of carbon when you're at the conditions of the Earth. Now, it doesn't happen over the time scale of a human life or many human lives, so for our purposes, diamonds are forever. But if you let them go for long enough, I don't know how long it takes, probably thousands or millions of years at least. If you let them go for long enough, your diamond, which you're so so proud of and so in love of, would turn into a black piece of graphite eventually. So luckily that doesn't happen too fast. So that's a phase diagram for carbon, which again just shows that it is possible to have two different solid phases, and typically you convert between those by changing the temperature or the pressure. In this case, you have to go to really high pressures to go from graphite to diamond. All right, so what we're going to do now with respect to phase diagrams is just a whole bunch of example problems to kind of give you an idea of the types of questions we will ask about diagrams. So we're not going to give you any diagrams that are any more complicated than what I've shown you, but we want to just know a little bit about how to read them and how to answer the types of questions that we would ask on homework questions and exams, which the last homework assignment will give you some insight into. Now, I forgot to check this before I came in. I think the last homework assignment is not going to be due on Sunday. We usually extend that until later in case there's still material to cover, which for us won't be an issue. I will double check that. You can always, I think in the homework assignments I put what the due date is in the information, so if there's any doubt about that. But at any rate, just so you're aware of that, you don't necessarily have to hurry to finish the homework assignment by Sunday. I think we should have extended that. So that's something that I just remembered, and I'll clarify with you a little bit later on Friday. Sorry, question?
So I have a question on so does altitude affect critical point?
Altitude? Well, it won't affect the location of the critical point. What altitude will affect is where you are on the phase diagram. So altitude affects the pressure that you have. So the phase diagram itself won't change at altitude. The critical point, the triple point will stay in the same place. But for example, the solid liquid line will be at a lower pressure, so the boiling point then would be lower if you're at the higher altitude. But it doesn't affect where the critical point is, no. All right, so then on to some example problems. So we have a phase diagram shown below, which is not for any real substance, just sort of a made-up one. So we want to know which phases are present at point A. So this kind of gets at some of the most basic ideas of phase diagram, which is labeling the different sections of the diagram for the different phases of matter. So as we should become familiar with, we have solid all the way on the left, liquid in the middle, gas on the right. And we're looking here for the phases that are present at point A. So point A is not on one of the phase change lines, so that means only one phase of matter exists at that point. It's not right on the line. And so the only one that exists then is in this region of the diagram would be solid only. So if you're on a phase change line, if you're on the border between two phases, both phases exist at that conditions. But if you're clearly off of the line in one section of the diagram or another, you would only have the phase of matter that exists in that part of the diagram. So for this particular one, it would be solid only. So that's a type of question we can ask just to make help you identify what's what the different sections of a phase diagram are. This one gets a similar type of question, but a little bit more complicated. So here we're looking for the phases that are present at point B. So again, it's always helpful to, before you start, label the diagram. This is one downside of doing Blackboard exams, that you can't label Blackboard, unfortunately, but you have to at least be able to visualize in your head where the different regions are, or crudely reproduce the diagram to see where they are. And then if we look at point B on this diagram, point B is right there, and it's right on the line between the liquid and gas phases. So at this position, when you're right on the phase change line, you would have both of those phases present, whatever it's the border between. So at point B, you would have both liquid and gas. So if it was a multiple choice question, you want to make sure you'd select both of those if you're on this particular phase change line. So that means at this position here, at point B, you would be in the process of vaporizing the substance from liquid to gas. So at those set of conditions, that pressure and that temperature, that would be a vaporization process for this substance where liquid and gas coexist. And if you increase the temperature beyond that, you would go exclusively to the gas phase, or if you decrease the temperature, you would go exclusively to the liquid phase from that position there. All right, any questions on those ones? Just identifying the different phases in a diagram. All right, so the next one here, we're looking at which temperature and pressure are closest to the triple point. So labeling the diagram yet again, same one, but we'll just keep labeling it so we don't lose track of where these are. The triple point is again the place where all three of the phase change lines intersect each other. So you have the solid-liquid line, the liquid-solid line, or sorry, the solid-liquid line, the liquid-gas line, and the solid-gas line. All three intersect. So that's that point here, and then we need to estimate which temperature and pressure that corresponds to. So the temperature goes down to the x-axis. So we see that that's in between 100 and 150, right around 120 Kelvin on the x-axis. And then if we go to the y-axis, we see that we're pretty much exactly at 0.6 atmospheres. So 0.6 atmosphere to 120 Kelvin, that's going to be, of these answer choices, choice A. So once we identify where the triple point is, we can see the temperature and pressure that corresponds to. And those temperature and pressures, again, they have some significance to them. So at pressures above that 0.6 atmospheres, you will not have any sublimation occurring. You can only sublime the substance below that pressure. And at temperatures above 120 Kelvin, you would also never see sublimation as you go in that direction as well. So that's the highest temperature at which you can sublime, and then the highest pressure at which you can sublime correspond to the triple point. All right, any questions on that? Yeah. So dot E would be called the critical point, and so what you do is you would I don't know if that question is asked about any of these, but we can jump ahead. So you would basically figure out what temperature and pressure that corresponds to, and so if you're at any, so you have sort of cordon off the diagram. Anything above that, as you go from bottom left to top right, would be supercritical fluid. So that is like point E is the last point where you can have a transition between liquid and gas. Anything that's at a higher temperature or higher pressure than that would be considered supercritical fluid. So for point E, you would sort of draw a box like that, where anything inside of this box, you would have two different phases, liquid and gas. Anything outside of that box over here, for example, would be supercritical fluid. At that point, you would still have liquid and gas coexisting, but anything higher pressure than that or higher temperature than that, you would no longer have two separate phases. Supercritical fluid is a little bit hard to wrap your head around, I agree. But I think that might come up a little bit later, so we'll see that in a future question. Any questions on this one or any other things about this? All right. So the next one here, we want to know what are the normal boiling and melting points for this substance. So we have to remember the definition for the normal phase change temperature. So remember that normal means we're talking about a pressure of 1 atmosphere. So that would be the melting and boiling points at a pressure of 1 atmosphere. So we're talking about this pressure here, 1 atmosphere. For the first time in my life, I drew a straight line the first try. And then what we have is we want to figure out the melting and the boiling points. So the melting point is going to be the intersection between the solid and the liquid line, or the solid and liquid regions at 1 atmosphere. So we go over to 1 atmosphere, 1 atmosphere, and that's going to be that point there. That point there. So we go 1 atmosphere, we find the intersection between solid and liquid, and then we extrapolate down to the x-axis to find out what temperature that corresponds to. So this point X that I've drawn here is going to tell us what the melting point is, and that's going to be around 110 Kelvin. Again, I don't have the axes labeled very precisely here, but we extrapolate down to the x-axis and we see that it's a little bit above 100, between 100 and 150, closer to 100. So I'll call that estimated at 110. So that's going to be the normal melting point. And then if we want to find normal boiling point, we have to go, again, still at 1 atmosphere, we go over to the liquid gas line and figure out where that crosses 1 atmosphere. So that I'm going to label as point Y here, which is our normal boiling point. And again, we extrapolate down to the x-axis to find the temperature, and with a little bit of estimation here, we'll call that 220 Kelvin. Obviously, you would pick the answer that's closest to that because it's not able to get exactly from this diagram. But anyway, it's around 220 Kelvin when we go down to the x-axis here. So that's how we identify the normal and the normal boiling point and normal melting points, is by figuring out where those two phase change lines cross 1 atmosphere of pressure, which is the pressure that we define for normal phase change temperatures. So questions on that one? All right. Continuing to see more and more examples of all the different things we can read from phase diagrams. So we want to know, what is the sublimation temperature for this substance at 0.4 atmospheres? So in this case, we're looking for the solid-liquid boundary. That's going to tell us where sublimation is occurring. Sorry, solid gas, geez. So we're looking for the boundary between the solid and the gas portions of the diagram. So that's this line here at the very bottom. And we go to 0.4 atmospheres, which is the pressure we're interested in. And so at that 0.4 atmospheres, that line, we go down and we extrapolate it down to the x-axis, which is 100 Kelvin. So at 100 Kelvin, we can sublime the substance if the pressure is 0.4 atmospheres. All right, and we saw in an earlier question that the triple point was at 0.6. So in order to sublime the substance, you have to be below 0.6 atmospheres. So at 0.4, we can sublime it when the temperature is 100 Kelvin. And that would allow us to convert between solid and gas, or gas back to solid if we were cooling it down. So questions on sublimation? Okay. All right, this one is a typical type of question we like to ask in Blackboard. So we have, so imagine that you're studying this substance, and you're initially at a pressure of 0.2 atmospheres and 100 Kelvin. So we're starting at this part of the diagram. So labeling the different sections: solid, liquid, gas. So we're starting there in the point that I've labeled, that I've drawn in blue right here. And so at the start of our diagram, we're in the gas phase part of the diagram. And it wants to know, as we increase the pressure to 2 atmospheres while maintaining a constant temperature, we want to know which of the following lists the phases that will be encountered during this process. So we're going to start at this position here, and we're going to increase the pressure. So pressure is our vertical axis, so we're going to go straight up. And we're going to stop when we get to 2 atmospheres. So we stop right there. That's our stopping point. So we see that as we go through this process, once we get here to 0.4 atmospheres, as we said, that's where sublimation occurs, so we would go from gas to solid. So as we increase the pressure continuously, once we get to 0.4 atmospheres, we cross from gas to solid. Then we're in the solid region of the diagram. And then once we get to about 1.6 atmospheres, which is this point there, we convert the solid into a liquid. So as we raise the pressure from 0.2 atmospheres to 2 atmospheres, keeping the temperature at 100 Kelvin, we're going to encounter all 3 phases, but the order of them is going to be gas first, then solid, then liquid. So that would be choice D here. We start out as a gas, we go into a solid once we go to 0.4 atmospheres, and then the solid gets converted to liquid up there. So all 3 phases, but in that particular order: gas, solid, then liquid. So questions on how I analyze that one? Okay. And then this one asks about the relative densities of the solid and liquid phases, which again comes from the slope of the solid-liquid line. So in this one, we all really care about the solid and liquid. So we see that the slope of that line is negative, and as that tells us, once we're in the solid, let's say here, right on the line, as we increase the pressure, we cross over from solid to liquid. We actually saw that in the last problem. If we were at 100 Kelvin and we increase the pressure, we cross from solid to liquid. So the phase that exists at the higher pressure, so as we increase the pressure, we go from solid to liquid, the phase that exists at that higher pressure is going to be the one that's more dense. So that means in this substance here, the liquid and the solid are in that order, liquid being more dense than solid. If this phase change line between solid and liquid was perfectly vertical, that would be where they have exactly the same densities. But in this situation, when it has a negative slope, as we increase the pressure, we convert from solid to liquid, telling us that liquid would be the more dense phase. Okay? Questions? Just stop me anytime. We're just doing a lot of these to get a good flavoring of the questions. Alright, and then the last, I don't know if this is the last one, I don't want to promise the last one. Yeah, this is the last one. Finally, we've beaten the dead horse enough. Alright, so the last one here is, what is the vapor pressure of this substance at 250 Kelvin? So another thing that you can read from a phase diagram is vapor pressure. So we talked about the mathematical relationship last time between vapor pressure and temperature. We know that vapor pressure increases with temperature. And by looking at the boundary between the gas and liquid phase, we can read off what the vapor pressure is. Because remember that the process of boiling, the process of going from liquid to gas, occurs when the vapor pressure is equal to the atmospheric pressure. And so this boundary line then tells us vapor pressure. So if we're at 250 Kelvin here, we go up to where there's that borderline between gas and liquid, and we see that those cross right around a little bit above 1.2 atmospheres, I guess, if we're being real precise. So we're like right there, which is just above 1.2 atmospheres. So that means at 250 Kelvin, the vapor pressure is equivalent to that pressure, which is 1.2 atmospheres. Or another way of interpreting that point in the diagram is that if the atmospheric pressure was 1.25 atmospheres, the boiling point of this substance would be 250 Kelvin. So it works in both directions, but we can read vapor pressure off by figuring out what the temperature is and figuring out where does that temperature cross the liquid gas line. And that pressure that corresponds to that would be the vapor pressure of that substance at that temperature. All right, so that takes us to the very end. Any last questions on phase diagrams? Yeah. Phase equilibrium, maybe not using that terminology. So phase equilibrium is a situation where two phases of matter exist or simultaneously, or sometimes three phases of matter. And that occurs anytime you're on one of these phase change lines. So if you're at any point in the diagram that's on one of these lines, you would be in a situation called phase equilibrium where two phases exist simultaneously. But I don't think we'll use that exact terminology because we haven't really learned what equilibrium is precisely in this course. And then if you're at the triple point, you'd have a phase equilibrium between all three phases. So you should be familiar with those concepts, but the terminology equilibrium likely won't come up. Any other questions? All right, so what we're going to do with the rest of today is we're going to just review some of the topics that I think are some of the ones that give people the most trouble. This is my opinion just from talking to students, so I may or may not be accurate reflection of what you think. But we're going to go through some of those. Now, the first thing I want to do in that regards is sort of wrapping up a lot of things we talked about in Chapter 9, which is classifying the different types of solids. So we've talked about several different kinds of solid phases and some of the different properties that result from those solid phases, some of the different structural features. And we just want to kind of wrap this all up and summarize it in one hopefully convenient table. So the first one that we talked about in detail were metallic solids. So metallic solids is one type of atomic solid, a solid that's made up of only one type of atom. And so when you have a metallic solid, the components that are present, or what we would call the lattice points, the points in the crystal structure that repeat themselves over and over again, those are all going to be metal atoms. So we saw that metallic solids have a number of different possible structures. We talked about some of the common ones, those three cubic structures as well as the hexagonal. And those lattice points, those positions that repeat in those unit cells or repeat over and over again throughout the crystal, would all be just individual metal atoms in that case. Now the requirement is, how do we identify what kind of substance is a metallic solid? It's just anything that has only one type of metal or only metal atoms in it. So if the substance is just a metal, sodium, potassium, magnesium, or any of the transition metals, iron, cobalt, ruthenium, whatever, If it's a metal, it's going to be a metallic solid in its solid phase. Now, one thing we didn't talk about in this course, I don't think it came up at all, is alloys would be another type of metallic solid. So an alloy is a mixture of two different metals together, but like I said, I don't think we cover that, so don't worry about that, but that's another type. Now, what are the forces that hold these atoms together? So another thing that's important to think about is we have all of these atoms held together in the solid phase, and what's responsible for keeping them locked into those positions in the solid. Because remember that solid phases tend to be very rigid. You don't have a lot of motion of the atoms and molecules in those phases. So what are the forces responsible for holding metal atoms together in a metallic solid? Those would be what we refer to as metallic bonds. And we talked about the nature of those metallic bonds being this, what we call sea of electrons. So it's these loosely held valence electrons that are shared between all the nuclei in the metal. They're delocalized over the entire metal. And those attractions between those delocalized electrons in the nuclei are what are responsible for holding those metal atoms together. So as I said then, examples of these would be any metal on the periodic table, sodium, iron, or other main group metals like lead. Just any metal would be an example of a metallic solid. And they have these metallic bonds that hold them together, and we learned about earlier some of the key properties then associated with that, which would be high conductivity, malleability, and so on. All right, so that's one type of solid. The next one that we talked about was a network covalent solid. So network covalent solids, there's two different types. So some network covalent solids are atomic solids, meaning they only have one type of element and then one type of atom. Others are network covalent compounds, which means they have two different elements in them. Now, because the word covalent appears, we should recognize that these are going to be composed of nonmetal atoms. So we talked about way earlier in the course when we talked about covalent bonds that it's nonmetals that form covalent bonds with each other. So if you're going to have a network covalent solid, you would have nonmetal atoms that are part of that solid. And then the requirements are, as I kind of already said, you can only have nonmetals present in the crystal, in the substance. Sometimes just one nonmetal, or sometimes a binary compound with two. So there's, as I said, two different types: atomic solids and compounds that can exist as that. The forces that hold the atoms in place, and the reason why these solids have some very specific properties that we talked about, is that what you have in these solids is covalent bonds holding everything in place, and those covalent bonds extend out in all directions. So you don't have discrete molecules, you have an extended network of covalent bonds that goes on forever, and that's what holds everything together in a network atomic solid. So because you have these really strong bonds holding everything together in the solid, you would expect these to have very high melting points, and indeed they have some of the highest melting points of any known substance. Now there's basically only about 4 or 5 different network covalent solids that you guys should recognize, because it's not always easy to look at the formula of a compound and tell, is this a network covalent solid or is this just a molecular solid, because both of those involve nonmetals. So the ones that you should be familiar with are both forms of carbon, which is graphite and diamond. So both of those are considered network covalent solids. These would be specifically atomic solids because they only have carbon in them. The other group 4 elements that are not metals, so silicon and germanium, which are metalloids, those have the same structure as diamond, would also be classified as network covalent solids or network atomic solids more specifically. And then the only compound that we introduced that's a network covalent compound would be SiO2. Now there are certainly other ones out there, but at least are the ones that we would give you on test. As long as you can remember that SiO2 is a network covalent compound, that's going to be really the only compound that would fall into this category. Again, we talked about the reason for this being that pi bonding is very weak between silicon and oxygen, so instead of forming silicon-oxygen pi bonds, it's more favorable to form a network of covalent bonds that goes on in all directions. Another classification, which we didn't talk about a ton of details with these in terms of structure, are molecular solids. But as the name implies, the components of a molecular solid, the lattice points, the points that repeat over and over again as you go through the solid, these are going to be discrete molecules. I hope I spelled discrete right. I always mess that up. So they're discrete molecules. You have individual molecules that then are repeated over and over again throughout the structure. And again, a requirement for this is that they would be composed of only nonmetals. And then the forces that hold them together, you don't have any sort of chemical bond between the components. You have these individual molecules, and then it's going to be intermolecular forces that hold these molecules together in the crystal. So those would be just intermolecular forces, which we saw that there's 3 categories. Dispersion, dipole, or hydrogen bonding forces are going to be responsible for holding these molecules in place in the solid. But they're relatively weak forces, so we would expect that most molecular solids have pretty low melting points. It's very easy to break those intermolecular forces of attraction and melt the solid into a liquid phase. So the examples of this are basically any of our polyatomic nonmetal elements. So I2, P4, and S8 would be molecular solids at standard conditions at room temperature. Any other diatomic molecule like nitrogen, oxygen, chlorine, fluorine, those ones are gases at room temperature, but if we cool them down enough, we would form a molecular solid from them. So if those are in their solid phases, any of those polyatomic elements would be considered molecular solids. Because again, they have discrete molecules that have 2 or 4 or 8 atoms, and it's those molecules that are then repeated over and over again throughout the crystal. And then many covalent compounds, pretty much any covalent compound that's not SiO2, you would expect that to form a molecular solid as well whenever it's in the solid phase. So if you had frozen water, ice, or if we took any other covalent compound and we cooled it down to a low enough temperature to get to the solid phase. Most small molecule covalent compounds are liquids or gases at room temperature because they have those weak forces, but if we go to a low enough temperature to make them into a solid, they would exist as molecular solids. So in solid water, which is ice, you have H2O molecules, you have hydrogen bonding between those H2O molecules, and you have these sort of regular repeating hexagonal water units that are going over and over again through the ice structure. And it's those hydrogen bonds that sort of hold it together. So those are molecular solids. We didn't talk a lot about structural details of those, but you should be able to recognize what they are and some of their features. And then the last one, which I think is the easiest to identify, are ionic solids. So the lattice components in ionic solid are just the ions that make up the compound. And as we've already learned way back in Chapter 3, if you want to identify what is an ionic compound, it's a combination of a metal with a nonmetal. Or in some cases, a metal with a polyatomic anion. But I think we're pretty familiar now how to recognize an ionic compound, and we would expect that any ionic compound, any common ionic compound, would exist as an ionic solid. So in this case, again, you have very strong forces that are holding the ions in place. You have ionic bonds between all of the oppositely charged ions that are present. So ionic compounds also have very high melting points because you have to break those very strong ionic bonds to be able to melt the substance. And then there's many examples of ionic solids. Any ionic compound that you can dream of would fall in this category. Common ones, of course, being things like sodium chloride, magnesium oxide, magnesium chloride. So for the first category and the last category, the metallic and the ionic solids, we learned some pretty in-depth information about the structures of those. We learned the different cubic lattices that metals exist in. We learned about how we can fill some of those holes to form ionic compounds. So for those ones, you're going to want to have the most detailed structural information that you're able to comprehend before the final. For the rest of these, the main thing we want you to do is be able to identify them and know some things about the properties that are derived from the arrangements of the atoms and molecules that you have in these different types of substances. All right, so any questions on how we classify solids or anything on this table? All right, so the last thing we're going to do is just sort of take a trip down memory lane, and obviously we're going to see a lot of all these topics as we go through the final review. But to get ourselves oriented, I want to start with some of the topics that seem to be the most vexing for Chem 1331 students. And this is pretty much true from year to year. I mean, this is the 4th time that I've taught this course, and these same topics are seen to be the ones that I answer the most questions about on a year-to-year basis. So we'll want to pay special attention to these as we go through and review for the final. So one thing that always causes a little bit of difficulty, both when we introduce it and then when it comes back again on the final exam, are the trends for ionization energy and electron affinity. So we know the general trend. All of us, I think, are going to remember this one, that both increase as we go left to right on the periodic table. And they both also increase as we go from the bottom to the top of the periodic table. So those general trends, this holds for ionization energy and electron affinity. We all, I think, are pretty familiar with that as we go across the periodic table. But the part that always sort of gets people on these is remembering where the exceptions occur. And you know, it's when you first hear about that, every time you hear the word exception, you sort of you sort of freeze up and have a little mini freak out, I guess, because you're like, oh no, there's exceptions. To understand where these exceptions occur, we have to think about what the stable electron configurations are, because both of these properties, ionization and electron affinity, refer to either losing electrons if we're talking about ionization energy, or gaining electrons if we're talking about electron affinity. So if you have a stable electron configuration, you're not going to want to add or subtract electrons from that. So the stable configurations that we should be familiar with are when we have a completely filled S subshell. So that second column of the periodic table where you have an NS2 valence configuration. That would be beryllium, magnesium, calcium, barium, strontium. Maybe I went in the wrong order, but those ones there that are in the second column of the periodic table have the NS2 configuration. And then the half-filled P configuration. So if you have a P3 configuration, that's a particularly stable configuration. Again, there's a lot of quantum mechanical reasons why this is that we're not going to worry about, but you need to remember that a half-filled P subshell is a particularly stable electron configuration. So the elements in that column, nitrogen, phosphorus, arsenic, and so on, are going to have that half-filled P configuration and have a very stable configuration. And then, of course, the one that's the most stable is the noble gas configuration, NP6. So once we've completely filled the P subshell, and we go to that last column of the periodic table where you have helium, neon, xenon, and so on, you're going to have that stable configuration. So those are the three stable configurations that we want to be familiar with. And when you're in one of these configurations, you don't want to gain or lose electrons. And that's sort of the key point of then understanding where the exceptions to these trends are. So that the atom in these configurations does not want to gain or lose any more electrons. It wants to stay where it is. So the exceptions for the ionization energy and the electron affinity occur in the same parts of the periodic table. They just work in the opposite direction. So ionization energy refers to loss of an electron. So when you get to those groups that have stable configurations, your ionization energy is going to be exceptionally high. So groups 2A, which have the NS2 configuration, groups 5A, which have the NP3 configuration, and group 8A, which is the noble gas, these have exceptionally high ionization energies because these don't want to lose any electrons. That means you have to put a lot more energy into the atom to be able to pluck off that electron. So they're exceptionally high in those columns. Now, the exceptionally high ionization energies for noble gases doesn't really matter because those are all the way to the right anyway. So those being the highest doesn't really throw off the trend at all. But the two real exceptions in the trend then occur at group 2A and group 5A, which are higher than you would expect them to be based on their location in the periodic table. And then the exceptions for electron affinity occur in the same place, but it's in the opposite direction because electron affinity refers to the desire of an atom to gain an electron. They're typically negative numbers. When we say that something has a high electron affinity, that means electron affinity is a large negative number. That means it wants to gain an electron more. So at those parts of the periodic table, it's going to be exceptionally low electron affinity when you have a stable configuration. Because again, those configurations you don't want to add any more electrons either. So for groups 2A, 5A, and 8A, those same columns of the periodic table, you have exceptionally low electron affinities. And really for noble gases, we don't even discuss electron affinity because those don't want to gain electrons at all. They're not even very well defined in that case. So those are where those breaks in the trends occur. And so then what's helpful then is to think about sort of a graphical representation for this, where I'm going to draw, as we go across the different groups of the periodic table, the basic trend that we see for ionization energy and electron affinity. So I'm going to first show in blue, I'm going to show the ionization energy trend. So I'm going to try to draw this as accurately as possible. So let's say for ionization energy, we start here at group 1A. We expect the ionization energy to increase as we go from left to right, but we see that group 2A is going to have an exceptionally high ionization energy. So it's going to come higher than we expect, and we would have then a decrease between group 2A and group 3A. Alright, so you have this exceptionally high ionization energy for group 2A. Between 3A and 4A, we would expect it to increase. Now, another important point is that we would never expect group 2A to be higher than one that's two groups over from it. So there's going to be a slight dip in ionization energy as you go from 2A to 3A, but then it goes back up where group 4A has a higher ionization energy than 2A. Group 5A is going to be an ionization energy that's, again, exceptionally high, such that we'll, again, have a slight decrease as we go from 5A to 6A, and then they're going to increase the rest of the way. So 6A to 7A increases, and then, as I said, the noble gases have ionization energy that sort of are even higher than you expect them to be, but that doesn't matter. That's the farthest to the right. There's no exception there. So if we draw a trend line for this, we can see that there is sort of this general, almost linear increase in ionization energy as we go across, but these two here, group 2A and group 5A, sort of lie above the general trend. They're exceptionally high, which means between 2A and 3A we have a decrease, and between 5A and 6A we have a decrease in ionization energy. So those are the places where the two exceptions occur, where the ionization energy does not increase as you go from left to right. And then electron affinity is sort of the same story, but as I said, the electron affinities have sort of the opposite trend. So as we go from 1A, where should I put this about here? So I'll do ionization energy in red, sorry, electron affinity in red, we're doing that now. So there's sort of a general increase left to right for electron affinity as well. But as we go left to right, again, group 2A has an exceptionally low electron affinity. It's actually really low because it doesn't want any electrons at all. So that's going to lie below our general trend line. And then we go back up for group 3A. We have an increase in electron affinity between 3A and 4A. But then again, group 5A has an exceptionally low electron affinity, so that comes way down. So group 5A and group 2A are way below the trend in this case for electron affinity. And then as we go to 6A and 7A, those come up again. So again, most of them fall on this left to right trend, but group 2A and group 5A have lower electron affinities than any of the elements surrounding them. And then the noble gases have just exceptionally low electron affinities, not even very well defined. We don't even usually think about those. But again, there's these breaks in the trend at both group 2A and 5A, but they go in opposite directions. The ionization energies are higher at group 5A and group 2A than you expect them to be. The electron affinities are lower in those groups than you would expect them to be. But they occur in the same spot in the periodic table. Alright, so any questions on that? Alright, the next thing I want to quickly review is all the different ways we can determine moles. This kind of ties a lot of things together that we've learned, starting in Chapter 5 all the way through Chapter 8. We talked about all different kinds of mole conversions. And so for a lot of things that we're doing in chemistry, whether it be stoichiometry being the big one, but also thermochemistry, also a lot of other topics that involve moles of substance, we have to be able to convert different quantities into and out of moles. Okay? And there's basically 4 ways now that we learn how to do this. So the definition of a mole that we introduce, which doesn't get used a lot in a practical sense, but is still an important one to know, is that we can relate moles to the number of entities that we have, where the entities being either the atoms or the molecules, whatever makes up that substance. So if we know the number of entities that we have, the number of atoms or molecules, if we want to convert that into moles, we divide by Avogadro's number. And if we want to convert number of moles of substance into number of entities, figure out how many atoms or molecules we have, if we know the moles, we can then multiply by Avogadro's number. You can move that over a little bit so it's continuous. So multiplying or dividing by Avogadro's number converts between number of entities and moles. The one that we probably used the most often was the relationship between moles and mass. And I think most of us are comfortable with this relationship now, but just to quickly review and summarize it, if we know the mass of substance and we want to convert into moles of substance, we divide by the molar mass. And then the opposite is true if we want to convert back from moles of substance into mass of substance, we multiply by molar mass. And keep in mind that these relationships, these first two that I'm doing, apply to any type of substance. So just because we're talking about an ideal gas, which has its own special relationships involving moles, doesn't mean that you can't relate moles and mass of substance in the same way we do for any other substance. So these two are pretty much universal. Number of densities, mass of substance, you can use for any type of substance you're talking about. Now, the two other types that we learn are specific for different categories of materials or substances. So if we're talking about solutions, usually aqueous solutions in the context of this course, if we know the volume of the solution, we can use molarity to convert between that and moles. So the molarity that we learn, which is moles per liter, only applies when we have substances that are dissolved in solution. So that's a more specific one that we use a lot in Chapter 6, but it can come up in other contexts as well. And so if you want to go from volume to number of moles, you multiply by the molarity, capital M is abbreviated. And then in the opposite direction, if you have the moles of substance and you want to determine what volume of solution does that correspond to, you divide by the molarity. And again, the way we approach these typically was to use molarity as a conversion factor, moles of substance per liters of solution, and then that allows you to convert between moles and liters. All right, so you have these relationships when you have aqueous solutions, and then the most recent one we talked about were ideal gases, where if we have the pressure, volume, and temperature of an ideal gas, if we know those parameters, we can convert into moles or back into one of these other relationships using that famous equation PV equals nRT. And so this is one we used a lot in the last chapter, Chapter 8, when we were doing, especially with gas stoichiometry, using PV equals nRT to convert pressure, volume, and temperature into number of moles, and then back into one of those parameters if we knew the number of moles. So these are the four different relationships we learned for number of moles. Sometimes we'll use them in combination with each other. Sometimes we'll use one of them separately. But this is kind of what we have right now. And as you're doing problems that involve moles, especially stoichiometry problems or and other things related to that, you want to make sure you have all these relationships in mind and know when is appropriate to use them and how we use these to be able to convert into moles of substance. So any questions on these types of ideas that are going to come up in a lot of different contexts? All right. The last thing I want to review are just some properties of chemical bonds, specifically covalent bonds, and some of the different trends we have with respect to those properties. So where is that in my notes? Maybe I'm going to have to wing it. Let's see. All right, so here we go. So there's two properties we talked about for covalent bonds, bond length and bond strength. And so there are going to be potentially types of questions that will ask you to rank the following bonds from shortest to longest or longest to shortest. So asking you, what are the relative bond lengths of these different covalent bonds? And there's two factors that influence that. The first one, which is the first thing you want to look at, is bond order. So the bond order influences the bond length. So if we have a single bond, which is two shared electron pairs, there's going to be an inverse relationship between bond order and bond length. So double bonds are going to be shorter than single bonds. Triple bonds are going to be even shorter than that. And this comes into play if we're just comparing bonds where we tell you the bond order, or if we give you, let's say, two diatomic molecules like B2 and N2, and want to use molecular orbital theory to figure out what the bond order is and then relate that to bond length, where there's sort of an inverse relationship. So the higher the bond order, the smaller or shorter the bond length. So that's an important relationship. And this is the one that you want to look at first, because going from a single bond to a double bond to a triple bond is a huge change in bond length. So for example, with carbon-carbon bonds, if you go from a single to a double bond, you decrease the bond length by about, I can't do math in my head today, about 20% or so, and then it's about another 20% decrease when you go from double to triple. So a really big change every time you increase the bond order. The more subtle effect on bond length is the dependence on atomic radii. So if we're comparing two bonds that have the same bond order, So 2 single bonds or 2 double bonds or 2 triple bonds. Then we have to think about the atomic radii of the atoms that are involved in that bond. So we compare atomic radii when we have bond orders that are the same. And essentially, if you have larger atomic radii, that's going to result in a longer bond. And that I hope makes intuitive sense to us. So if we compare carbon-carbon bond to silicon-silicon bond, the silicon-silicon bond, which is, so silicon is larger than carbon, it's below it on the periodic table. This one we would expect to be the longer bond. So they're both single bonds, but because silicon is larger than carbon, you'd expect the distance between the 2 nuclei to be larger in silicon versus carbon. So when you're comparing bond lengths, look at the bond order first. That's typically the more important factor, especially if you're comparing things that are in the same row of the periodic table, where if you have, you know, a nitrogen-nitrogen single bond versus a carbon-carbon triple bond. Yeah, so carbon is larger than nitrogen, but the triple bond is a more important factor than that, so you would want to pick the one that's the higher bond order if you're comparing things that are similar to each other in terms of their atomic radii. Now, the other property of bonds that we have is bond strength, or what's also referred to as bond energy. So again, the definition is the enthalpy change. Now that we know what enthalpy change is, we can use that terminology to describe this. It's the enthalpy change associated with breaking 1 mole of a bond. So we introduced the concept of bond strength back at a period of time when we didn't know what enthalpy changes were and we didn't know what a mole was, so it was kind of a weird time to introduce this concept, but now it makes hopefully more sense. The enthalpy change associated with breaking 1 mole of a bond. And so if we have a bond AB, it would be the enthalpy change associated with taking this bonded AB pair and separating it into separate A and B, where again the delta H for this process is equal to what we call the bond energy or bond strength. And then there's a relationship between bond energy and those other parameters, bond order and bond length, and both of them are inverse. So if you have a higher bond order, you would expect there to be a higher bond energy or a stronger bond. So if you have to break 2 bonds in a double bond versus 1 bond in a single bond, you expect it to take more energy to break the double bond. So as you increase the bond order, you're going to increase the amount of energy required to break that bond. And then there's also then, so those two are directly related. The other one, though, which is inversely related, is bond length. So if you have a shorter bond length, meaning the 2 atoms that are bonded together are closer to each other, that will correlate with the higher bond energy as well. So bond length and bond energy, just like bond length and bond order, are inversely related. The shorter the bond, you'd expect it to be stronger. And that's because the nuclei are closer together, so you have a stronger attraction between the nuclei and the electrons that are shared in the bond, and that means it requires more energy to break them apart. So I think those are some of the topics that I identified as being ones that we always had a lot of confusion on. Of course, there may be others that are percolating in your head, so we'll certainly address those during the final exam reviews that are coming up. So we'll meet one more time on Friday, which of course is optional for the review session, and then our very last official meeting for class will be Monday, where we'll also just be doing review. All right, I'll see you guys hopefully on Friday.